good morning, good afternoon, or good evening. My name is Piet Zaalberg, and thanks for tuning in from wherever you are. In this session, I will talk about the relation between cobble revetments, sand, and overtopping. Let's get started. In 50 years' time, the surface level of the North Sea will have increased by 0.4 meter. So we need to increase insight into how our coastal protection performs. Not only to sea level change, but also in its physical environment. In 2013, the latest extension of the Port of Rotterdam, the Maasvlakte 2, was completed. Here is Rotterdam, here you see the Port of Rotterdam, and the Maasvlakte is approximately right there. It consists of an 11-kilometer long sea defense, of which 3.5 kilometers is an innovative dynamic cobble revetment with a foreshore of reused concrete blocks. You can see that bit right over here. If we look at satellite photos, this one is taken in 2013, just after when it's finished. And if we look over time, we can see that sand is washing in, moving from southwest to northeasterly direction. And if we were to stand right there on the cobble revetment, it would look like that. Here you see not a lot of sand between the cobbles, but if we look there and we walk to that location, you see that sand is covering the rocks, but also in between the rocks. One of the failure mechanisms for cobble revetments, or revetments in general, is overtopping. What is overtopping? Overtopping happens when waves break on cobble revetments and wash over. This is measured by a volume per unit time per unit length. It's denoted by the symbol Q. My research question was, what's the influence of a decrease in porosity and cobble layer thickness on the overtopping as a result of sand washing into a cobble revetment? My approach. First, analyze the physical experiments that were conducted during the design phase. As many physical model tests have been conducted, looking into the stability and cross-shot transport balance of the cobble layer. Less so on the influence of sand completely filling the pores of the cobble revetment, which is happening right now. The verification criteria of the experiments at that time were that during the test, the sand underneath the cobble layer does not disappear. Secondly, the wave overtopping does not exceed a specific discharge limit. And finally, that sand underneath the cobble layer does not wash out. This has been conducted in many experiments, of which I like to highlight two, which is the one depicted here, where no sand is washed in the cobble layer. And here you see the cobble layer, which is placed on top of a sand core. And furthermore, where 50% of the thickness of the cobble layer has washed in with sand. So I did not have the opportunity to test in these wave facilities, since they're expensive, takes a lot of time. Also, their availability is very limited. So I aim to reproduce these experiments numerically and validate my numerical results with the test conducted during the design phase. After careful evaluation, I opted to go for OpenFOAM, which is an open source field operation and manipulation based on C++ for the development of customized numerical solvers. The library Waves2Foam is a toolbox for OpenFOAM used to generate and absorb free surface water waves. Currently, the method applies the relaxation zone technique. A large range of wave theories are supported, and the relaxation zones can take arbitrary shapes. It is originally developed by Niels Gool-Jacobsen. In 2014, the porosity module was developed to model the interaction between free surface waves and a permeable medium in collaboration between Bjarne Jensen and Niels Go Jacobsen. Here you can see the numerical setup of the experiments conducted in the TARES, including the relaxation zones, cobbles, and sand core. Note that all the numerical cells within the sand core are cut away. That saves computational time. And we can do this because the sand is impermeable over a wave period. The irregular wave field is generated based on linear superposition of the individual frequencies in the wave spectrum. A total of 100 wave components together make up the John swap spectrum. The frequencies are non-equidistantly distributed with a higher frequency resolution around the peak of the spectrum than at the tails. This enables a better time domain representation of the exceedance statistics of wave height and wave periods for a small number of frequencies. With this, the waves to foam does not model sediment transport. Therefore, we need to average the overtopping results of the cross-shore profile measured before and after the physical experiments in the wave flume to obtain reliable results. Also, part of this was a thorough mesh sensitivity study and a study to compare the incoming waves in the physical test with numerical tests. They all matched well. So, to get to reproduce the test in the right way, we used two cross-shore profiles. One that was measured before the physical test, being test S2T3, and one after the physical test, being S2T4. We both ran these experiments numerically and averaged the overtopping, as cross-shore morphology is not included in the waves to foam package. So if we do that with the first experiment, where no sand is washed in, we obtain an accuracy, a numerical accuracy, with respect to overtopping of 13%. For the second experiment, where half of the cobble layer was washed in, we obtained an accuracy of 1%. Thus, we can say that our numerical wave flumes are now validated. Now it's time to carry out various numerical experiments to test our theory. But first of all, we need to quantify the process of sand washing in between the cobbles. And how can we quantify that? Well, if we look at porosity, the porosity can be defined by the volume of pores divided by the total volume of our control volume. And sand does two things. It changes the porosity, and the sand level within the cobble layer can change if all that sand falls down. So you can say that the cobble layer actually decreases in thickness. So the bounds of the influence of porosity of the cobble layer on the average overtopping discharge, Q, are calculated. The maximum and minimum values measured in the field have been assigned for the whole numerical porous cobble layer to quantify this effect. Then we've done a range of experiments where the effective thickness of the cobble layer was increased, actually decreased as the sand level within that interfaces increases. Finally, we decrease the effective thickness of the cobble layer of a composite profile consisting of two straight slopes by decreasing the level of the cobble layer. So we ran all these experiments numerically, obtained the average overtopping discharge, and now we're going to try and interpret these results and come up with a relation. And here you see the thickness of the cobble layer depicted by the symbol TC, thickness of the cobble layer. And here you see how we define the infiltration length, which is the length water can infiltrate tube over one wave period. And the total pore volume of the layer can only be filled with water when the maximum infiltration depth over a wave period is larger than the effective thickness of the cobble layer. Pores that lay deeper will not be reached by the water within a wave period and will therefore not contribute in reducing overtopping volumes directly. The developed theory is that a part of the volume over every wave run-up tongue is sinking into the pores of the cobble revetment and does not overtop. The wave overtopping volume is thus reduced by the total volume of pores that can be infiltrated over a cycle of a wave. This is a similar approach to Steeg and Bredler and Provost, which they wrote a paper about in 2016. And the total pore volume per meter width can be calculated by this formula. So the length of slope times the thickness times the porosity, or as a function of the crest height. And to gain insight useful for other projects and scales, we can divide the pore volume number by the spectral wave height squared. If we set that out against the relative overtopping, we can find a very interesting relation, which is this. And you see that it holds up very nicely. The composite slope cases with the thickest cobble layer here is plotted above the trend line as the relative overtopping rate is quite large. That can be explained by the fact that the thickness of the revetment is larger than the infiltration length. The relative pore volume number of the porosity and deltaris cases is comparably large as a result of the increased crest height and large porosity, which you can see here. But it's associated with the smaller relative overtopping as the pores are more easily infiltrated with water. Though it is noted that as a result of the stability number scaling to determine the cobble size in the deltaris experiments, which is linear, the infiltration depth isn't scaled correctly as this scales quadratically. So, as I just discussed, that the infiltration rate suffers from scale effects because stability number scales linearly and flow resistance as a result of Darcy-Forsheimer scales quadratically. So these experiments overestimate overtopping rates when compared to real life scale. The profile shape is largest uncertainty. And the conclusions. Open foam can successfully reproduce experiments, which can save money. New insights in the physics of overtopping. And my suggestions for further research are these 3 points. Stimulate more scenarios, rescale the model, and conduct new physical experiments with high temporal and spatial resolution. Bye, and thank you for joining this session. I hope you have enjoyed it.